We have here a recursive sequence. That's one in which, in order to know a term, I have to know its preceding term. In this case, the sequence is defined by a sub 1 is equal to 1, a sub n plus 1 is equal to 3 minus 1 over a sub n. We are asked to show that this is increasing and that a sub n is less than 3 for all n. That will mean that it's monotonic and bounded. So by the monotonic sequence theorem, we're going to conclude that it's convergent, and then we're asked to find the limit. We're going to proceed using mathematical induction. We're going to take these separately. First, we're going to show it's increasing, and then we're going to show the inequality a sub n is less than 3. To use mathematical induction, we want to show that it's true for some number, usually 1. In this case, we're going to show that it's true for n equals 1. And if n is equal to 1, then we're looking at a sub 1 is equal to 1, and a sub 2 is equal to 3 minus 1 over 1. That's coming from the recursive definition. Of course, that equals 2. So a sub 2 is greater than a sub 1, which means that it's increasing for the first two terms, but it's true for n equals 1. The next step in mathematical induction is to assume that the statement is true for some k. And so assuming that a sub k plus 1 is greater than a sub k, we will then show that it is also true for k plus 1, and that will conclude the inductive proof for this. Well, if a sub k plus 1 is greater than a sub k, then it follows that 1 over a sub k plus 1 is less than 1 over a sub k, because reciprocals reorder numbers. But now I want to tell you what we're going to do. We're going to build an expression that looks like 3 minus 1 over a sub k, and we're going to do it on both sides. We're going to use a series of if and only if statements, as we saw before. To build 3 minus 1 over a sub k, I'm going to multiply both sides by a negative 1, which is going to have the effect of, again, reversing the inequality. So negative 1 over a sub k plus 1 is greater than negative 1 over a sub k. That's true if and only if 3 minus 1 over a sub k plus 1 is greater than 3 minus 1 over a sub k, which is another way to say, but I'll use an if and only if, that a sub k plus 2 is greater than a sub k plus 1. Almost forgot about that last little bit, because what we have on the right is the expression that gives us a sub k plus 1. And if you think about it, you'll notice that we have on the left is an expression for a sub k plus 2. So just a recap of induction. Show that it's true for some number, usually n equals 1. Assume that it's true for some number k, so you write down something about assuming. And then show that that assumption being true for k makes it also true for k plus 1, and that's the inductive step. Tie a little bow on this portion of it. We'll say, thus, the sequence is increasing. Now we go to the next part. The next part is show that a sub n is less than 3 for all n. Oh, let me go back to one thing. I didn't use a derivative here, right? If we want to show that something is increasing, we could differentiate and show that the derivative is positive. I can't use a derivative for a couple of reasons. Number one, I don't have a continuous function, right? This is a sequence. But number two, and it's more important, I can't just turn this into an a sub x because this is a recursively defined sequence. There's no function definition that I can give you that we could actually differentiate. So we didn't really have much choice but to use mathematical induction. Now we'll make the statement that a sub n is less than 3 for all n. Now, of course, that's not a proof, right? I'm just letting you know. It's a roadmap. This is what we're doing. Let's show that it's true for n equals 1. Well, a sub 1 is equal to 1. That's less than 3. I know, that didn't seem like much, but it's required. Now, let's assume that a sub k is less than 3 for some k. What we're about to do looks a whole lot like what we just did. Then, negative a sub k is greater than negative 3, which implies that, negative 1 over a sub k is less than negative 1 over 3, which implies that 3 minus 1 over a sub k is less than 3 minus 1/3. but 3 minus 1 over a sub k is another name for a sub k plus 1, and now we have that a sub k plus 1 is less than 3 minus the third. We could do the arithmetic, but the point is it's less than 3, and that's what we wanted to show. Put a little check mark, but I need to write a sentence. So a sub n is less than 3 for all n. Now let's put all this together. A sub 1 is equal to 1, and the sequence is increasing, and all of the terms are less than 3. Therefore, since a sub n is between 1 and 3, and a sub n is increasing, that is monotonic and bounded, the sequence is convergent by the monotonic sequence theorem. Since the sequence is convergent, it has a limit. To find the limit, let's call it L. So we're going to write down that the limit as n approaches infinity of a sub n is equal to L. Folks, it would also hold true that the limit as n approaches infinity of a sub n plus 1 would equal L. So L, this is going to be weird, is equal to 3 minus 1 over L. Where is this coming from? The L on the left is from the limit of a sub n. The one on the right, the 3 minus 1 over L, is the expression for a sub n plus 1. We've just plugged L, the limit, in place of a sub n. If we clear the fraction and manipulate this equation, then we end up with L squared minus 3L plus 1 is equal to 0, which is a quadratic function. We can't factor it, but we can use the quadratic formula. And so L is equal to 3 plus or minus the square root of 9 minus 4, all divided by 2, or L is equal to 3 plus or minus the square root of 5 over 2. But as it turns out, 3 minus the square root of 5 over 2 is less than 1, and a sub n is greater than or equal to 1, so they can't add up to a number less than 1. So we conclude that L is equal to 3 plus the square root of 5 over 2.